This is video number 1 for sections 2.3 and 2.4, the Postal Service problem. This lesson is very much a let's put it all together kind of lesson. We're going to return to the linear models that we looked at the start of the chapter. We're going to incorporate now our new function notation, our f of x notation. We're going to talk about how to use these models to answer questions, and we're going to think about the meaning of the slope and the intercepts of our linear models. Let me start out with a scattergram problem here. This is the scenario is somebody is interested in studying the U.S. Postal Service and specifically how much mail they've been delivering during several years. And so you can see here in the table, someone has collected some data for various years from 2007 to 2011. And then here's how many billions of letters the post office delivered during those years. And just a glance at the table, of course, tells you, gee, over this period of time, the number of letters definitely went down. And we know, obviously, that's because of things like email or electronic bill paying or things like that. Well, we're going to analyze this using a linear model. If we're going to use modeling, then we need a couple of variables and we need to be very specific about what they mean. Sometimes we get to pick the definitions of the variables, sometimes they're given, and in this case they're given. So two variables, n, it says, stands for the number of letters in billions, and t stands for how many years it's been since the year 2000. So all of that is provided for us. You'll notice that next to the n, here's our new function notation, n or f of t. In other words, those are interchangeable in this problem, kind of like how y and f of x are interchangeable. So n or f of t, whichever way you want to call it, that's the number of letters, t is the time. So that means we have to make a little bit of adjustment to our data. We're not going to actually use the years. T stands for how many years since the year 2000. So of course that would be 7 years here, 8 years for 2008, and so on down the line. How about the second row? Let's see. That stood for number of letters in billions. In other words, this 95.9 means 95.9 billion. Well, that's exactly what the variable definition says. So I don't have to adjust those numbers at all. I can simply fill them in. Okay, so those are all filled in, and what's next? Well, normally what would come next is making a scattergram of this data so that you can do two things. Number one, verify that the dots, kind of look like they fall into a straight line. And number two, decide which 2 points to use in terms of to find the equation of the line. Well, I've done that already to save us some time in this lesson. And I can verify, you can check it out as well if you want to, but I verified that yes, this looks like a fairly linear pattern. And I chose out, based on the picture, these two data points as the best ones to use to form the equation of the line. And so letter B basically says, look, let's make sure in our adjusted data that we circle those 2 points. These are the 2 points, the 2 ordered pairs that we're going to use in order to create our linear model. And that's where we're going next in part C. So part C says, now go ahead and find the equation using those 2 points. It might help you to rewrite the points as ordered pairs just to make it look more familiar to you. And then we're going to take these 2 ordered pairs and write the equation of the line that goes through those 2 points, and that will be our linear model. This is just the same math we've been doing over and over. We're going to have to find the slope first, so I'll do my little slope calculation. Second y minus first y, and second x minus first x, and then obviously reach for the calculator. And I get negative 17.7 on the top and then 3 on the bottom. And then dividing that on the calculator, I get negative 5.9. The directions say round final values, meaning your final slope, your final y-intercept, round those values to 1 decimal place. This one actually came out perfectly to 1 decimal place, so I don't have to do any rounding. If I had to round, I would have rounded it off to 1 decimal place. Okay, so I've got my slope. And then I look back at my points, and I'm kind of disappointed because neither one of them has a 0 in the x position, so I don't have the y-intercept. I was not given the y-intercept, which means I'm going to have to find it. This is where we've learned 2 different methods. You're welcome to use whichever of those methods you like. I think I'll just go ahead and use the y equals mx plus b method, right? That's the one where I fill in the slope, and then I temporarily plug in one of the points. I'll just use the first one, I think. Temporarily plug in one of the points for x and y, and then solve for b. So again, a little bit of calculator work here. That comes out to be negative 41.3, and then to get b by itself, I would just have to add that 41.3 to both sides. And when you do that on the calculator, you get a final value of b equals 137.2. Okay, so I have my slope, I have my y-intercept. That means I can write the equation down. It would be y equals negative 5.9x plus 137.2, right? Y equals mx plus b. I'm not quite done because the directions of the problem do remind me, hey, there wasn't really an x and a y in this problem. There were 2 other letters, so I'm going to have to go back and remind myself what those are. I always do my work just using x and y like we did here. I just find that's easier on the brain to do. But then at the very end, you do need to make sure you put in the correct letters. Let's see, that's where I go back to my let statement. And it was n for my y variable, and then t for my x variable, for my independent variable. So n and t. So then in my final equation, my final answer to part C, I would simply use those correct letters. So n equals negative 5.9t plus the 137.2. We're saying this linear model, this equation, does a reasonable job of describing the amount of mail that was delivered by the post office during those years that we looked at in the table. There is a reminder note down below here that I should point out. Remember, the tricky part of this in my math lab is that, of course, every student may pick a different couple of points to choose when making the line. So you might get a different answer than somebody else in the class. And so what they do, just as we saw before, is they'll give you the equations in a multiple choice format. So you pick your 2 points. You do all the work we just did, you come up with your equation, and then when you go to put that answer in my math lab, just select the one choice. There will always only be one choice that's close to the numbers you found. Like maybe they would have negative 5.8, maybe they would have 139, but there will only be one choice that's close to what you found. Choose that one, and then for the rest of the problem, make sure to use their equation when answering the other questions. Okay, let's continue here though. Part D says, now take this equation you just found and rewrite it using our new fancy function notation. This is not difficult to do. Remember, the let statement told us that the letter n was interchangeable with f of t. Don't write f of x. We don't have x in this problem. We have t. But n and f of t are completely interchangeable. So here would be the function notation way of writing the linear model. And that's all I'm being asked to do here in part D. Now that we have that, let's use it a little bit. Let's answer some questions. So part E is a math question. Find f of 16. Let's find it, remind ourselves how to do it, and then in part F, we'll try to connect it to some real life meaning associated with the post office problem. Okay, f of 16, we know that the number in the parentheses is what's going into the function. And in this function, t's are going in. So that 16 is a t. f of 16 means replace all the t's with 16. So I'll do that, and then after that, there's nothing really to do in terms of work other than grab the calculator and type it all in, and there's not really any great reason why I shouldn't just type that all in at once. I'm getting 42.8 off the calculator. So we're saying that f of 16 is equal to 42.8. Well, what does that mean? What does that have to do with the post office situation? Well, when you write one of these sentences, you have to take into account both numbers. You have to take into account the starting number, the 16, and you have to take into account the ending number. So we better figure out what these things mean. 16 what? Well, remember, 16 was a t. And if I've forgotten at this point what the t was, I just go back up to the let statement. Refer to this statement all the time. What was t again? Oh yeah, t stood for how many years it's been since the year 2000. So we're talking about 16 years since the year 2000. In other words, we're talking about the year 2016. So my sentence is going to start off in 2016 ... right? Then we're saying something happened. Well, that's where the other number comes in. If 16 is the t that's going in, then of course 42.8 is the n that's coming out. What was n again? Well, if you look back up at the let statement, you remember that n stood for the billions of letters that the post office was delivering. So basically what this statement is saying is, in 2016, the U.S. Post Office delivered 42.8 billion letters. Is that true? Well, I have no idea, and that's not really the point. The point of these questions is to say, if our linear model is correct, in other words, if the pattern we noticed during the years in that table continued on, what would have happened? And we're saying, boy, at the rate at which their deliveries were going down, if that same thing continued by 2016, they would have been down to 42.8 billion letters. And you can see how people use math then to make predictions about some future events if the current trends continue.